This is CS1101 Lecture 10.2. We're going to continue looking at a few coding examples and ways to sort. Specifically, we're going to be looking at the selection sort. The first coding example we're going to do is going to reverse the elements of an array. So the last element becomes the first becomes the last. The code that we write needs to be able to work for any size of an array, so it needs to be generalized. So it doesn't need to work for arrays of length 6 or with a only odd number of elements or something like that. It needs to be general to work for all possible arrays of various sizes. A lot of times when you're trying to code with an array, if you're needing to do some sort of a swapping or order-based method, it may be best to draw out a simple array and visualize what you actually want to do to it. So we wanted to reverse this array. What we're really wanting to do when we say reverse it is we want to swap the first and the last element as pairs, then swap the next elements moving in one from the edges, and then finally swap the middle. Of course, in general, for any given length of array. So we're wanting to increment in from the left by 1 and in from the right by 1, swapping the contents each iteration through the loop. So does this work? We have our array defined and we stored it in this number array variable. And we have written a for loop that starts at the element 0. It'll process every element of the array. And it stores the current element into temp, then puts the value of length minus 1 minus I. So remember, for an array of length 6, like this, the maximum element, or the maximum index, is going to be 5. So the maximum index in an array is always the length of the array minus 1. Because the length is the total number of elements, but we start counting, or we start indexing from 0. So this is going to be index 5, which is going to be given by length minus 1. So this gives us the last element of the array, and this minus I allows us to progress from the right side as we progress from the left side. So we're assigning the next element on the right side of the array to the next element on the left side of the array. So visualizing this, going back to our little visual, so we are at I equals 0, and we are at I equals length 6 minus 1 minus 0. When I becomes 1, I equals 1 I equals 6 minus 1 minus 1, that's 4. I shouldn't say I equals for this side, but I think you understand the point I'm making. So this is element 0, which is given by I when I is equal to 0. When I is equal to 0, element 5 is given. So we swap the contents of element 5 and 0 by storing element 0 into a temp, taking element 5 and putting it into element 0, and then taking what we stored in that temporary variable and putting it into element 5. Simple enough. But we've made a mistake that we need to point out. So we're processing from 0 to the length of the array. So that means that using this algorithm that we have defined here, we take the outermost elements of the array and swap, and then move into the next elements. So visualize what's happening. So when I equals 1, we swap these two. Or sorry, when I equals 0, we swap those. I equals 1, we swap these. At I equals 2, we're done. We've swapped each pair of elements. But our code is not done, because we're not going to stop at 2. We're going to stop at 5. So if this code continues, so we are already done. We've swapped everything. However, if we continue swapping, I equals 3, what's it going to swap with? Is it going to read past the end of the array? No. Length 6 minus 1, 5, minus 3 is 2. So it actually swaps what has already been swapped. Then at I equals 4, it swaps another pair that's already been swapped. And then finally at I equals 5, we completely have swapped the array and unswapped the array. The simple reason is just because there are half as many pairs of elements as there are elements individually. So when we process every element of this array, we're actually processing every pair of this array twice. So we don't want to process from 0 to the length of the array. We want to process from 0 to the number of pairs of elements in this array. So let's change our code so that we only process the number of pairs of elements in this array. Here we go. So now, rather than processing from 0 to length, we're processing from 0 to length divided by 2. This will allow us to stop at 2 rather than progressing all the way through 5. So our total length is 3, which means we will process 0, 1, 2. So we'll go through this loop once with I equals 0, I equals 1, I equals 2. At the end, when we update to I equals 3, we will do this test. Is 3 less than 6 divided by 2? No. It's equal to it, but it's not less than it. So then we don't continue this loop and we exit. So this will allow us to swap each pair of elements in the array in the way that we wanted. Now here's another example. What if we wanted to rotate the array? Rotating is a lot like shifting. So we want to shift this array left, but we call it rotating because when we get to the end and 3 shifts off into the negative index, it should rotate around to being in the ending location, like this. So 38975 becomes 89753. That's why this would be called a rotate left. Now, the question that you need to answer in your mind is, do we move each element starting from the right or starting from the left? Remember, we're wanting to shift every element to the left. So where do we begin to process? Do we begin processing at the 3, or do we begin processing at the 5? So I would recommend starting from the left, since we are shifting left. So you start from the left. We will store this 3 into some temporary location. And then we will move element 1 into element 0, element 2 into element 1, element 3 into element 2, and element 4 into element 3. And then finally, we will take the value we stored in temp from element 0 and store it into element 4. Again, we should generalize this so that it works for any size of array. So we need to make use of the .length field so that we are able to process an array without actually knowing the size of the array beforehand. So here's some code that we think might work. Let's notice. We are taking the first element of the array and saving it to our temporary variable called remember me. Then we are going to process the rest of the array using a for loop. Now notice the interior code in this for loop. We are assigning the value stored in element I plus 1 into element I. That's going to shift every element to the left. But think about this. If we allow I to take on the maximum index, so in the case of an array with 6 elements, the maximum index is 5. So if we allow I to have the value 5, and we attempt to access element 5 plus 1, we're exceeding the length of the array and we're going to have a runtime error. So we need to make sure that I never goes beyond the value length minus 1 minus 1, right? Because length minus 1 is the maximum index, and if we allow the maximum index plus 1 to be used as an index, that's going to attempt to access past the last element. So what we need to do is say that I always has to be less than array length minus 1. So now, if array length were 6, as in a 6-element array, so the maximum element index is going to be 5, we are only going to process indexes 0 through 4, because 6 minus 1 is 5, and this statement is only true for I less than 5, not less than or equal to. Okay? So this will process 0 through 4, and we won't wind up reading past the end of the array. But that leaves the last element unset, so we need to take our temporary value that we saved from the first element and store it into the last element in the array. So this works for a left shift. What about a right shift? It might be a little trickier if you think about it. It might seem like it should be the same difficulty, but it's a little bit different, because instead of shifting I plus 1 into I, we're needing to shift I into I plus 1. So that's going to require a different processing order. We're having to process the array from right to left instead of left to right. So we would need to count from the right side of the array to the left side. So we would need to count backwards, is what I'm saying. We would need to start counting at array length minus 1 and count down to 0. Instead of worrying about a shift right, we'll leave that for you to play with. We are going to look at inserting an element in a sorted array in the proper location. So we want to write a method that will insert some value into an array while maintaining the sorted order. So we are assuming that ARR is already sorted. So since we're wanting to change the array object and not create a new array, we are going to delete the last item, because obviously if we add one item to an array length of 6, the array length should become 7. Instead, when we insert this new item into the array, we are going to delete whatever item is pushed out into the new index. So think conceptually about what we're trying to do. We have some array here, 1, 3, 7, 10, 12, 15, 22, 47, 74, and we want to insert the value 11 into that array, keeping the sorted order in the array. We're going to have to insert it at element 4. So algorithmically, we need to find the correct insertion point, insert the value, and then whatever was occupying element 4 through whatever was occupying the length -1 -2, we want to shift to the right and store in those element locations in the array. We don't have to worry about length -1 because we're just going to drop him. He's going to occupy a position beyond the length of this array, and so we're not going to include him. He gets dropped. We could write a program to return a new array that has the original length +1, but what we want to do is modify the existing array object. So we'll have to get rid of one of the values. Since we had the array full and we're adding another element, we're going to have to toss one, and the one that we're choosing to toss is the final element. So let's look at this insert in order method. We have parameters ARR, which is our integer array, and then we have the value that we want to insert into this integer array. Now, keep in mind we're assuming the ARR is already sorted. We initialize a position pointer, and we're going to use that pointer to figure out where in our array we should insert the value in. Then we have a while loop that we're going to use to figure out where we should insert this value in. We're going to process this while loop as long as our position is less than array length, right? Because we don't want to try to access an element beyond the end of the array. That's a runtime error. So we need to make sure we're not going past the end of the array length. And we're going to keep processing as long as n is greater than the element at index position. So whatever value is stored in position, that is the index to our array. And we are going to continue to look for where we should insert as long as n is greater than what we're currently looking at. So if we had an array that was populated one, 2, 3, 6, and n was equal to 5, position equals 0. Is that less than the length of 4? Yes. So that's okay. Is n greater than the element stored in index 0? Yes. 5 is greater than 1. Okay. Position equals 1. Is that less than array length? Yes. Because the array length again is 4. So yes, 1 is less than 4. Is 5 greater than 2? Yes. we're now looking at position 2. Is 2 less than array length, which is 4? Yes. Is n greater than the value stored in this position? Yes, 5 is greater than 3. Move to the next position. Now position equals 3. So we do keep processing. But is n greater than the value stored at 3? No, it is not. So we will immediately exit this while loop and go to the next set of statements, leaving the value of position equal to 3. So notice what we found is that we went from being greater than to less than. So when that occurred, when we found the first element that we were less than or equal to, we found our insertion point. So we didn't modify position. Once we found this location, we immediately exited. So position equals 3. That's where we should insert this value. So yeah, this is a good way to search for where we need to insert. This works. Position is equal to array length. Why would that be a problem? Why would we want to just do a return? See what's happening here? If position is equal to the array length, we return nothing because this is void. We can still use the return statement to terminate execution of our method. Well, how would we wind up with position equal to array length? If in our previous example we had 4 elements in this array, and we said we were inserting the number 5, if this value had been 4, then there would have been no element that 5 was less than. So when we processed position 3, we would have said, is position 3, is the value 3 less than array length? No, the array length is 4. Is n 5 greater than the value stored in that location? 4? Yes, it is. So we would have executed the statements in this while loop, and we would have incremented position to be the value 4, which would point to here. So element 0, 1, 2, 3, 4. We're now pointing past the end of the array. So this checks to make sure that we were able to find a valid array position. If position is equal to array.length, that means we didn't find a place to insert in this array. So this deals with the possibility where we don't find an appropriate insert location. Now we need to set about shifting the elements to the right so that there's an opening for inserting our value in. To do this, like we mentioned previously, when we're doing a right shift, we have to start processing from the rightmost element of the array. So this is something a little different. We're going to use a for loop that counts down instead of a for loop that counts up. So we're going to initialize I to be the last index. So array length minus 1 is always our last index. And we're going to continue to process as long as I is greater than position. And we're going to update I after each execution of our loop by subtracting 1. So what we are going to then do is take element I minus 1 and store it into I. So this takes the element just to the left of the last element and stores it into the last element. So drawing this out, this is element I, this is element I minus 1. We take the value stored in I minus 1 and store it into I, which deletes the value in I. We didn't save it off, and we don't want to. We said we were going to drop it. And this will progress until I is no longer greater than position. So if our position that we're going to insert at is here, that's our insertion point pointed to by position. Then we will process I equals 0, 1, 2, 3, 4, 5. So this has a length of 6. 6 minus 1 is 5. So we start at 5. Our position has a value of 2. We'll process I equals 5, update I equals 4, move this element into the right, I equals 3, move the value currently stored in our insertion point to the right, I equals 2, 2 is not greater than 2. So we will not continue to execute. We will jump to the statements following our for loop, and we will store in our insertion point. So we've talked about that Java has this arrays.sort method built into the arrays class. So if we declare some array called strings, so this is an array of type string, so each element of this array is a string, and we print this array using the toString method, we'll see exactly what we typed in, CBGHDFEA. It's exactly how we typed it in and initialized it. But then if we call the arrays.sort method and pass the array strings as the parameter, sort is actually going to change this array and reorder it. And it doesn't return a new array, just like we've been doing. It has an effect on the actual object pointed to by the location stored in this variable. So then when we print out the array again, using the very same statement that we used previously, we see that the array is now in alphabetical order. So that's great. And when it's exactly what you want, it's perfect to use. However, it doesn't do everything that you might want. It performs a very specific function. It puts things in ascending order. So what if we wanted descending order? Or if we're dealing with strings, this is going to care whether or not it's uppercase or lowercase. What if we want it to disregard case and put it in alphabetical order? Well, that method does not perform those functions. So we often have to write our own sort routines. But the good news is that most sorting techniques can be easily adapted to suit modifications. So as long as you understand the ideas behind how to sort something, you can apply those ideas to whatever situation you find yourself in to be able to satisfy the new constraints. So if we wanted to be able to say sort based on alphabetical order without considering case, if you understood the general approach to sorting, you can modify that general approach to accomplish that goal. So if we use the built-in sorting routine in the arrays class to sort the following set of strings, so the following array of strings, it's going to put them in uppercase first, followed by lowercase. So notice, it's in alphabetical order, but uppercase occurs before the lowercase. So Charlie, Delta, Zulu, then lowercase Alpha, Bravo, Echo, Golf, Hotel. So what if we wanted this to ignore case so that it was strictly alphabetical? How could we code such a sorting routine? So writing a sorting routine can be difficult. So it's not a trivial task. But there are several approaches to sorting, some of which are faster but harder to understand, and some are a bit slower but more straightforward to grasp. So we're going to start with one of the easier algorithms called selection sort. It's not as fast as many other approaches, but it is straightforward to understand. Selection sort is going to arrange the elements by looking for the smallest element and storing that in element 0. Then finding the next smallest element and storing that in element 1. And so forth until it has reached array length minus 1. So for each array element, it's looking for the smallest remaining value. So when the whole array exists, it looks for the smallest value in existence and stores it in element 0. Then it locks element 0. It no longer considers it. Then it starts looking for the next smallest, and it stores that next smallest value in element 1. Then locks element 1. So forth. So we are going to wind up with a sorted array in ascending order. So we already know how to write code to find the smallest element in an array. So we're going to make use of that code, make use of that idea of finding the smallest element, and what we're going to do is make several passes down the list just like we described. So when we're looking for the smallest element, we'll store it in element 0, then lock element 0, then we'll search for the smallest in the remaining array and store that in element 1. So we're going to successively search this shrinking list for the smallest element, and each time storing it in the subsequent array location until we have reached length minus 1, which we do not need to process, because if we have put every smallest element in all the preceding index locations, we know that the only value left must be the max value, the largest value, so we don't have to do anything to the last element. So let's use our knowledge of searching for the minimum value to code this selection sort. But a couple of notes here. Think about this. When we say we're going to put an element from the array into element 0, what we're actually saying is we're going to swap it, right? Because we can't just insert it. That'll make the array grow. And we don't want to return a new array. We want to have the effect on the existing array object. And we can't just overwrite the value that is stored in 0, because then we're going to lose that information. So we must swap the value that we find to be the lowest with the value which is currently stored in element 0. Then we'll repeat this, finding the smallest item among the remaining elements and swapping into the correct location of the array. So we're going to find a minimum value, store it in the first array location, lock that array location so it can't be changed, and then move to the next array location, which would be element 1, find the minimum value in the remaining array, swap that value into element 1, lock it, rinse and repeat. Each time we find a minimum value, or we are processing the array to find the minimum value, we're going to call those a pass down the array. And we, as we mentioned, will stop making passes when we're down to one item, because we don't need to process the last item, as we know it must be the maximum remaining value. So let's talk through an example execution from a visual perspective. So first of all, we have an unsorted array. We know the general process. We're going to do a pass down this array looking for the smallest value. When we find the smallest value, we're going to swap that value for the value in element 0. So 7, 6, 11, 17, 3, 15, 5, 19, 30, 14. Minimum is 3. We swap 3 into element 0, so 7 goes into element 0, 1, 2, 3, 4. So 3 goes into element 0, 7 goes into element 4. And we can see that effect here. Now, we need to look for the next smallest value. This is locked. He doesn't change. So in the remaining array, we look for the next smallest value. 6, 11, 17, 7, 15, 5, 19, 30, 14. So we had to pass down the array again. 5 is the smallest value. We're going to swap 5 into element 1. So that means 6 goes into the location which was previously occupied by the value 5. So now we have the first two elements locked in place. And then we would pass down the array again and find the next smallest value, which would be 6. And we would swap it with 11. We would continue this process until the only remaining element in the array was the last element. When only one element remains to be locked, we are done. Because if only one element remains, it must be the maximum element in this array, based on the algorithm that we have applied. Because if we're always searching for the minimum value, when we reach the end and have only one value left unlocked, that means it is what's left over after successively searching for the minimum value. Therefore, it must be the max. Let's look at one more example. So given this initial array, 27, 63, 1, 23, 64, 58, 14, 9, we know what to do. We search the array for the smallest value, and we're going to store it in element 0, 1. So we have to swap 1 into element 0's location, and the value stored in element 0 gets swapped into element 1's, or the number 1's location. So that's what we see here in our first pass. 1 was swapped into element 0, and the number 27 was swapped into the location previously held by 1. Second pass. 1 is locked. We're not looking in this first array location. We start processing at 63. What is the smallest value left? 9. So we're going to swap 9 into 63's location and 63 into 9's location. We see that in the second pass. We searched, we found it, and we swapped it in the second pass. So next, in the third pass, we're going to find our next smallest, which is going to be 14, and we will swap 14 into the next array element. So we swapped it into element 0, then we swapped it into element 1. Now we're swapping this next smallest into element 2. So 14 goes into element 2, 27 goes into the element which was previously occupied by the value 14. Picking up where we left off, we searched that array, found that the next lowest value was 23, but 23 already occupies the next element, so we didn't have to swap it. We search for our fifth pass and find the next lowest is 27. We swap 27 into the element 4. So the value 64 goes into the location previously held by the value 27. We search for the lowest in the remaining array. It's 58. But 58 is already in the next location, so therefore we don't have to swap anything. Then finally, we search the remaining array for lowest value. It's 63. We swap 63 into the next location. And then we realize, okay, there's only one element left. So we're done. So when you have populated all the elements of the array except for the final element with the minimum values, you know that whatever is left must be the max. So we're done after processing elements 0 through whatever the maximum element is minus 1. So n minus 1 elements. So here's a mini exercise to verify that you understand how selection sort works. Take a moment, pause the video, and see if you can write down what the fourth and fifth passes will look like given a selection sort of this array. So we've already completed the third pass. We've locked element 0, 1, and 2, so we've done 3 passes. Write down what the array will look like after the fourth and fifth passes. After the fourth pass, the array will look precisely the same as it looks now. The reason is because we searched for the minimum value in the remaining array locations. The minimum value is 23, and it's already in the third element. So we don't have to change anything. Nothing gets swapped. So 23, 64, 58, 27, 63 is going to remain the same. So we know that these options are incorrect because of the fact that they already have 27 manipulated. In the fourth pass, nothing changes. We're setting 23. So now let's evaluate these other two options. What happens in the fifth pass? Well, in the fifth pass, the same thing happens that in every other pass happens. We look for the minimum. In this case, it's 27. And we swap it into the next array location. So the result would be 23, 27, 58, 64, 63. 23, 27, 58, 64, 63. So we have our correct fourth pass. And now we have our correct fifth pass. Here's some code that will implement selection sort. We have an array called A being passed in as a parameter. We have a for loop here that will process this array n minus 1 times. This is the number of passes. So this implements number of passes. For an array with 5 elements, so a length of 5, we need to make 5 minus 1 passes, so 4 passes. So this goes from 0 to length minus 1, not from 0 to length. 0 to length would give us n passes. 0 to length minus 1, while I is less than length minus 1, gives us the number of elements minus 1 passes. So this allows us to appropriately pass over this array the number of times necessary to successfully selection sort it. So I is our selection. So our first element that we have selected is 0. And we assume, as just an initial guess, that the smallest value is stored in our current selection, so I. Why? Because in subsequent passes, we're not going to check element 0. So when I equals 1, we'll assume that the smallest is in 1, and then we'll check every element after 1. So this is how we lock elements which we've already sorted. So on the first pass, I equals 0, so we say we'll start looking for the smallest in element 0. That's our naive guess. And then we're going to check and see if we're right. And if we're not right, we will adjust what our current smallest is. So we say for j equals I plus 1. So we initialize our counter inside this nested for loop to be our current selection plus 1. So we naively guessed that our smallest was in the current selection, and then we're going to start searching in the next element to see where the actual smallest is in the array. And we'll search from that next element to the end of the array, processing every element to see where the smallest is. So this is simply a find the min. That's all this is here. This code finds the min in the unsorted portion of the array. That's all this does. And what gets stored in smallest is the index of the smallest value. Once we've found that smallest index, we are going to swap the value stored in the current selection with the value stored in the smallest index. So this puts our next smallest value into our current selection. And this is the typical swap logic that we've used multiple times. And then we start over on our next pass, now with our selection at 1. So this implements exactly what we have walked through visually. Make sure you understand how this code works and think about how you might extend it to be able to sort something from largest to smallest.